looking at exponential functions and particularly growth and decay. So here's two graphs of growth and decay. So exponential means they go up very fast, so there's going to be a curve to them. So this would be one of growth, and then this would be a exponential function of decay. Because it starts up high, and then it goes down and exponentially decreasing. When the growth starts out very low or at zero and increasingly gets higher and higher as it grows. Okay, in this equation for exponential functions, this is the general equation. So A represents the initial amount or the starting amount that you're going to have in the problem. B represents the base or the multiplier, and we're going to see what that looks like. It's going to look a little bit different in a little bit here when we're looking at growth and decay. X stands for the number of time intervals that have passed. So, like if I said it's gone past 5 years, or in 3 years what would happen, or 6 months, or whatever, that's what the X stands for. And Y stands for your final amount. How much is left, or how much has it grown since it started the initial amount. So here's our two equations that we're going to use our formulas. So the growth and the decay look very similar to each other, except one has plus because we're growing, and one has a minus because we will be decreasing. It is decaying. Alright, so in both of them, that's why I have this in black. Y always stands for the final amount that you ended up with. A is the starting or initial amount you start with, of course, in either one of them. R stands for the growth rate or decay rate, and it's usually in a percent form, but you need to put it in decimal form in the equation. And then X stands for the time intervals, how much time has passed from when it started to when you want to end up at, whether you're growing or decaying. So in the growth formula, one other thing, the 1 plus R in that formula is your growth rate, and in the decay, the 1 minus R is your decay rate. That's your decay factor. So it's a growth factor, 1 plus R, and your decay factor, the 1 minus R. Alright, so we want to see how much we have after 4 years. So our money will be growing, so we're going to use the growth factor, the growth formula. So it's going to be Y equals, then the A, which goes next, is your initial amount. How much did you start with? So I started with $1,000. Then it's 1 plus, and it's 6% per year, so it's 0.06 because you have to put it as a decimal. And the X up here, the time intervals, it's going to be in there for 4 years. So how much would I have at the end of 4 years? So then I have 1,000 times 1 plus 0.16 is 1.06 to the fourth power. And then I have 1,000. So 1.06 to the fourth power is approximately 1.26. So we'll go out to 2 decimal places. Then we take that times the 1,000, and we would get then approximately $1,262. So that's how much we would have after 4 years then. Alright, in this one you can see a cup of tea, green tea, has 35 milligrams of caffeine. The average teen can eliminate 12.5% of the caffeine from their system per hour. How much caffeine is still in the teen's body after 3 hours? So we're eliminating, so that means we have to use the decay one. So we have Y equals, how much are we starting with? That's the initial amount. We're starting with 35 milligrams. Then it's 1 minus because we're eliminating, getting rid of it, it's decaying. 12.5%, that's as a decimal, it's 0.125. And 3 hours, so it's a third power here. So then we have 35 times 0.875 to the third power. So that'd be 35 times 0.4488, and that's going to be approximately 23.45 milligrams are still left in their body after 3 hours, which is quite a bit. So caffeine has quite a bit of caffeine in it, so it's going to take a while to eliminate all that. Alright, so we're going to use the same problem as before. But this time we want to find out how many hours is it going to take until there's only 7 milligrams of caffeine left in the body. So before, we knew how many hours and what we started with, and after 3 hours, there's 23 milligrams about left in the body, but we want to know how many hours it's going to take for it to get down to 7 milligrams. So that's our final amount, so that's going to start with 7 equals 35, that's how much we started with in the caffeine in the body, and then 1 minus, and it's 12.5% per hour, but we don't know how many hours. That's our x. That's what we're going to try to find out. So we have 7 equals 35 times 0.875. The x there. And now we're going to divide by 35. Divide by 35. So that's now 7 divided by 35 is 0.2 equals 0.875 to the x power. So we've got to figure out that x, how many hours is that? And this is just a guess and test. So you're just going to have to take 0.875 to some power. So we know to the third power, it gives us 23. So we want to go up higher than that because we want to, since 3 hours is 23 grams, we know it's going to be higher than that. So you just guess and test until you get close to 0.2. So it would be 0.875 to some power, see if that equals 0.2. If it doesn't, you just keep on doing that until you get real close to 0.2. And you're going to find out that it's going to come out to be approximately, x will be approximately 12 hours. So like I said, if you take 0.875 to the 12th power, you should get something real close to 0.2. It's not going to be exact, but it's going to be close to that. So doing these types of problems just to guess and test on there. Unless you had it graphed, and then you could look at a graph. Alright, so let's say you bought a pretty nice SUV for $20,000, and it depreciates 15% per year. So what would be the value if you ended up keeping it for 10 years? Which actually you should, because cars are expensive and all that, so you want to keep it as long as you can so you don't have to have payments. So it's depreciating, so once again now we're going to be using the decay factor, just because it's going to be going down in value. So we're going to have y equals, and we're starting with $20,000. That's our initial amount. And then 1 minus, because we're depreciating, it's going down, 0.15, and 10 years there. So we're going to have 20,000 times 1 minus 0.5 is 0.85 to the 10th power. And then 20,000 and 0.85 to the 10th power is about 0.1969. And if let's do this. Multiply 20,000 times 0.1969. It's going to be worth approximately $3,937. So after 10 years, that's the only amount, or that's how much it's going to be worth, the SUVs, which is not much, but it's something. Alright, here's our last one here. So the attendance at a 20th basketball game of the season was approximately 1,200 people. That's probably pretty close to one of our games we had. From the start of the season, attendance increased by 5% per game. How many people were at the very first game of the season? Alright, so we know at the 20th one, so that's our final amount. So we had 1,200 people. What we don't know is the initial amount, because that's what we're trying to find out, the starting amount there. That's what the A represents. And then it's 1, and we're increasing, so it's going to be a plus because it's a growth. Exponential, and 0.05, and we're talking about the 20th, after 20 games. So we're going to have 1,200 equals A, let's do that in black, times 1.05 to the 20th power. And if I take 1,200, then I'll take 1,200 equals A, And 1.05 to the 20th power is approximately 2.65. It's not exact. We're just going to 2 decimal places. Now I'm going to solve for a, so we'll divide by 2.65, divide by 2.65. So a equals approximately, let's use approximate signs because it's not exact, approximately 450 people, 52 I think it is, or something like that. So the very first game, there's approximately 452 people there. That's not exact. Once again, we don't care about that. We just want an approximation. And it increased by 5% each year for 20 games. So after 20 games, there's about 1,200 people. And so that's what it started at. So that's a lesson on exponential functions, growth and decays. And we'll do some more of those on for a worksheet to get more practice. But go over these again, and good luck to you. Bam! I forgot one thing. I wanted to go back to this slide here, the growth formula and decay formula. In our original equation, or the general one, we had y equals a bx, and here you can see that the b has been replaced with the 1 plus r and the 1 minus r. So that's your base, that's your initial amount there, or your multiplier. So I just want to show that the b is the same thing in your general formula, a bx, and that 1 plus r and 1 minus r, those are your b's from the general to the growth and decay formulas.